Hey everybody, welcome to Rules of Inference with me. Today we're going to talk about deducing conclusions from the implication if P, then Q. May seem really straightforward, but we're going to find that there are a lot of different things that you can do with this. It means that we're getting really close to proofs, because if you say if these things, then you get this thing, that's like what all theorems are about. And it's like, here are these things that we can assume, we get something really cool. And it's a theorem because it's a big deal, because it's not obvious. And so we have to prove that somehow. And rules of inference is how we're going to get there. I'm not saying that there's some preordained formula that is going to guarantee success, because there is not. You cannot learn how to do proofs by following rules, memorizing formulas, or just reading a couple of examples. The patterns are many and sometimes very complicated, but I can give you an idea. So, very beginning. A proof begins with a premise, and that is the thing that we are allowed to assume is true. The conclusion is the statement that we need to prove. The big idea here is that we are going to operate on these premises using rules of inference until we arrive at our conclusion. Rules of inference, some of them are like really basic, and you've been using them for a very long time. So before we get into here are names and specific rules and tables and stuff, I'm gonna ask a question. Given that my cats sit by the window on sunny afternoons, and it is a sunny afternoon right now, what do you think my cats are doing? There they are. It is my sunny afternoon. There are my cats. They're sitting by my window. What that looks like, so there. We're sitting by the window. You have just used a rule of inference, and you probably didn't even realize that you were doing so. What we can do is we can say that we've got a P and a Q statement sitting in here. There we go. So cats sit by the window is one of them. And sunny afternoons is the other one. And sunny afternoons implies cats sitting by the window. So I said P implies Q. So if it's a sunny afternoon, my cats will sit by the window. And then I also told you it is a sunny afternoon right now. So this problem told us this was true, told us this was true, and then we naturally assumed that we could say that Q was also true. Okay. That has a formal name. It is called like Modus Ponendo Ponens. Doesn't even matter. I really don't care. But it's exactly what I just said. We knew P implied Q, therefore we assumed Q. We have words like and, we have the word assume. That means we can start translating these things into ands and conditionals right here. We can re-express this using quantifiers. So why does this line of reasoning always work is my next question. It always works because this right here is a tautology. Remember, a tautology is a proposition that is always true. So let's go ahead. Let's prove that this is a tautology. So this is just the truth table so far up to the conditional. You've seen it before. if we have P and the conditional, that means in order for it to be true, we need that to be true and that to be true. But then that's the only time they're ever going to line up, because when this is true, this guy's false. And then P was false for the other two. So there you go. So then now we're going to do the final column. So we've got, for the very first one, this is true. And this is true. Right there and right there. So that means overall it is true. But then remember, if the beginning part is true, or the beginning part is false, the overall statement becomes true. So because these are all false, we get that these were all true. And there you go. It's a tautology. And that's why our rule of inference works. In fact, all the rules of inference are going to be tautologies, and that's why these work, and we can use these for proof, or these lines of reasoning for proving things. I'm going to give you a new way to notate this. Okay. Moving on from the fact that this is a tautology, another way to denote this would be P then Q, therefore Q. This notation means you've got premise, therefore we can conclude our conclusion. Man, that's deep. Conclude the conclusion. That's helpful because if you like Google rules of inference, you're going to see everything get written this way. And everything above the like equals line right here is premise, and everything below would be the conclusion. So for example, you would see a table that looks much like this. Very first one, you'll see Modus Tollens. That is the one that we just went over. And then what my table has that I think is kind of unique, I was trying to find a table online to just copy, and I didn't like any of them. I have this little interpretation column, and I think that's basically all you need in order to understand these. For instance, Modus Tollens. If Q is a consequence of P and Q is false, P must also be false. Why is that true? Because remember, if P implies Q is like overall true and Q was false, that means we couldn't have had that P was true. Otherwise, we would have gotten that Q was true. That's basic thought behind that. Next one is just fancy transitivity. If P implies Q and Q implies R, you get P implies R. And then I'm not going to go through and read all these. This is in a handout. Go through and read each of these and make sure that you understand what this column is saying, except for like this guy. This guy is, we'll just say, not very important. I can't think of a time when I'd like use this to prove things. The rest of these show up plenty, and then as they show up, I won't have expected you guys to have memorized this, but this is very crucial for like a certain type of proof. And so when we hit that, I will remind you, hey, this is okay because blah, 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 rules of inference. All right. In addition to those rules, we also have quantification rules. So the first one we have is for all x, we get P of x. Therefore, we can assume that P holds for any C. It's true for everything. Therefore, it would be true for this specific case over here. That's basically what this says right here. For example, all kids are cute. Therefore, I can conclude that my child in particular is cute. Universal generalization means, let's say, I just pick an arbitrary, well, it's this example, for the sake of this example, pick an arbitrary kid. If any kid is cute, I didn't specify blonde kids are cute, kids that are 3 years old are cute. I didn't specify any of that. I just said any kid is cute. And if that's true, we can then conclude that it's always true. All kids must be cute. If any kid is cute, all kids are cute. And then for existence, we've got there exists a P and X such that P of X is true. Then P of C is true for some C. Not all of them, not an arbitrary C, for some C. There exists a kid that is cute, and then some kid is going to fulfill that role, and I'm going to tell you right now, my kid in particular is cute. Then existential generalization, again, these names, don't memorize them. You've got P of C for some C holds, therefore we have found an X that exists. There exists an X so that we'll get the statement P of X in particular. It's going to be that C because I already told you. So then again, example, my kid is cute, therefore cute kids exist. Because I found one, that must mean that they exist. Otherwise my child wouldn't exist. It's pretty darn cute. Okay, sorry for the mom moment, but there you go. We will use these. I will be sure to point them out as we use these. Again, this is not a memorization. This is a try and come to a mental understanding of, yes, I can see why this logic works. Okay, and along with the good arguments come the bad arguments. And I tried to put it into like 3 categories. First category we have is affirming the conclusion. So this means we are going to use some point. We're using the condition of the conclusion to imply our hypothesis. So we assume the conclusion to get to our hypothesis. And it's like, no, that's like circular backwards reasoning. For instance, we've got n is an odd number, and we know that if n is prime, then it is odd. Notice the arrow would point this direction. Prime implies odd. But then you turn around, you're like, oh, so if it's odd, that implies prime. It's like, no, that's going that direction. That's the wrong direction. You can't do that. For example, just to make sure that you understand, we've got 21 is an odd number. Or prime. Yes, so 21 is an odd number, but 21 is not prime. Denying the hypothesis. It's kind of like similar-ish. It's an argument that uses the negation of the hypothesis to conclude the negation of the conclusion. So if prime implies odd, then not prime means not odd. And just like, no, again, 21 is not prime, but 21 is odd. Taking this back to like real life, it's like saying, if it rains, then my driveway is wet. It didn't rain, so my driveway isn't wet, which is false. My driveway is wet all the time when I have no rain because my kid loves the hose outside and he will go and spray it up in the air and he'll stand underneath it and have fun for far too long. Okay, so these are examples where we made arguments that were not valid. So this is not a valid argument. This is not a valid argument. And I feel like those ones are like pretty obvious. We're getting to, the last one is, I think, maybe the most dangerous kind of a mistake. And it's an argument that is valid. So if n is prime, then it is odd. Let n be prime, then n is odd. So this is the modus ponens reasoning. P is true, P then Q is true, therefore Q. I can tell you though, something went wrong in here. Here's a counterexample. So this is a valid conclusion. But 2 is prime and not odd. But my reasoning was good, and so what went wrong? This guy right here. Most dangerous kind of mistake, or probably the most common kind of mistake that you're going to see here, is a faulty premise. You're going to assume things that you're not allowed to assume. Okay. So that's all I've got for now. Next time we talk, we will do some actual proofs. And let me know if you have any questions on the 2 tables that I gave, which will be in a handout that I post on Sakai. Anyway, bye for now.